My name is Hezro Da Silva, and today I'm going to be discussing the research project that I completed during the summer of 2020, which has to do with determining the decomposition of protonated glutamine. Glutamine is an amino acid in the human body, and it's a very important molecule because, like all amino acids, it is a building block of proteins. Proteins in turn make up tissues, which make up organs, which make up organ systems, which in the end makes up the human body. Here we have a ball and stick depiction of protonated glutamine. And I say that it's protonated because it has an extra hydrogen on the molecule here. The white spheres represent hydrogen atoms, blue spheres represent nitrogen, red spheres represent oxygen, and gray spheres represent carbon. Before I get into the details of the project, I'd like to thank Westminster College for funding, Dr. Jessica Johnston, my advisor, our collaborators at the University of Utah, Dr. Peter Armentrout and his research group, other students in Dr. Jessica's research group, Jordan Contreras and Rosa Mendez Ortega, for their work on deamidation, and the Center for High Performance Computing at the University of Utah for computational time. The decomposition of amino acids has been linked to diseases such as Alzheimer's, so it's very important for us to understand how these molecules break down over time. Glutamine specifically is also considered to be a molecular clock, and that's because it goes through a decomposition called deamidation at very specific genetically predetermined times in the body, so we can effectively use it as a biological clock. You can see the product of deamidation here on the right, and this figure is based off of my research group's data. My research today begins after deamidation has occurred. And this research is all computational in nature, so it was all done on the computer. And as a student who's interested in medicine, I find the application of this research on the human body in diseases such as Alzheimer's to be particularly interesting. Our collaborator at the University of Utah provided mass spectrometry data to us in which protonated glutamine, which in shorthand is H plus GLN, had been collided with xenon, XE in shorthand. Today I'll be picking up on the structure shown here on the right, which results from deamidation. Deamidation being represented by NH3 loss, NH3 being the formula for ammonia. I'll be focusing on two decompositions. The first, water and carbon monoxide loss following deamidation, shown here with the formulas H2O and CO. And the second, water and 2 carbon monoxides lost following deamidation. The goal of this research was to identify the mechanism or the series of steps by which these two decompositions occur. I used a computer program called Gaussian to computationally manipulate my starting molecule, and a program called GaussView to visualize those manipulations. I sent my calculations to the Center for High Performance Computing at the University of Utah, and I was able to do this research wherever I had internet access. I'd also like to review the concept of an elementary step, which some of you may have already learned in a general chemistry class. We visualize this elementary step using a reaction coordinate diagram, with the reaction progress on the x-axis and the energy on the y-axis. Shown here is a simple reaction coordinate diagram. It's not directly related to my research. I'm just using it as an example. So we see that the reactants undergo an increase in energy, called the activation energy, and pass through what is called the transition state. This is very important because if the reactants don't have enough energy to pass through this transition state, they will not turn into the final products. Here is the reaction coordinate diagram for the first mechanism, loss of water and carbon monoxide following deamidation. The energy of this diagram is relative, which means that it's being compared to ground state protonated glutamine. So it's as if we had set the energy of protonated glutamine to be 0. In the first elementary step of this mechanism, this group here on the right, called the carboxylic acid group, undergoes a rotation. This is followed by a rotation of the hydroxyl group on the left. And these two rotations disrupt a series of hydrogen bonds that were along this top side of the molecule, which help to lower the energy. Therefore, we see that the overall energy has increased. Next, we undergo a series of smaller rotations that are setting up the molecule for water and carbon monoxide loss. So here we're continuing with the last structure from the previous slide, and we see that we go through the highest transition state of the mechanism. Recall that if the reactants don't have enough energy to pass through this transition state, then they won't turn into the final products. This high energy transition state also determines the dissociation energy for water and carbon monoxide loss following deamidation. So we see that water completely dissociates from the molecule and is loosely bound to the 5-membered ring. This is followed by the dissociation of the carbon monoxide as well. And we see some energy differences here at the end. And this is simply because of interactions between the dissociated water, carbon monoxide, and the 5-membered ring. So here in this structure right here, water is loosely bound to the ring product, and the carbon monoxide is also interacting with the water molecule. And these interactions help to lower the overall energy. And that's why you see that the 5-membered ring is actually higher in energy by itself than this structure here. And that's simply due to the interactions between the respective molecules. And as we get to the final product, it doesn't matter the order in which water and carbon monoxide is lost. What matters is that we end up with the same final product, and that final product is lower in energy than the high energy transition state that we discussed earlier. Next, let's look at the mechanism of the further loss of carbon monoxide. So we're starting with the 5-membered ring from the previous slide, and we see that we undergo a rotation of this carbon atom here, which opens up the ring. This is followed by another smaller rotation, and this is followed again by dissociation of the carbon monoxide molecule. Again, we see the high energy transition state, which determines the energy needed for the reaction, and we get to the final product here, the 4-membered ring and carbon monoxide. And again, we see that the interactions between the carbon monoxide and the ring help to stabilize the overall energy, which is why the 4-membered ring by itself is higher in energy than this structure shown here. So today we have looked at 2 decomposition mechanisms following the deamidation of protonated glutamine. The first being water and carbon monoxide loss, which occurs at a rate-limiting step of 288 kilojoules per mole. And the second being water and 2 carbon monoxides lost, which occurs at a rate-limiting step of 459 kilojoules per mole. These dissociation energies are in good agreement with mass spectrometry data provided from our collaborators at the University of Utah, and the final structures are also in good agreement with results published by other researchers on the subject. So we can be confident that these mechanisms that were developed are accurate and reliable. Thank you for your time.